The second section in dynamics is called forces in two dimensions. Now this section is significantly less complicated than the tension questions that we did in lesson 1. So relax a little bit. Here we go. You're pulling a 10 kilogram box on a level surface. The magnitude of the force you exert is 40 newtons, and it's directed at an angle of 30 degrees above the horizontal. We're supposed to assume a frictionless surface and calculate the acceleration of the box. So here's our box. It is 10 kilograms, and we are pulling it something like this with 40 newtons, and that is 30 degrees above horizontal. Okay, there you go. And the question is, what is the acceleration? This is a force question, and so we're going to use F net equals ma. But we have to recognize that the direction of the acceleration is not going to be in line with our force vector over there. If you think about pulling something at an angle like this, you generally don't pull things up into the air when you do that. When I think about pulling my kids on a sled, I'm always pulling the rope at an angle like that, but never have I lifted my children into the air on that sled. Right? So the acceleration is not going to be directed upward at a 30-degree angle. The acceleration is going to be directed horizontally, like this. That's the acceleration. Now this is not a force vector. I'm just pointing out the direction of the acceleration. So when we are using F net equals ma to figure out the acceleration of that box, we need to recognize that the acceleration is going to be in the x direction. And so we can't use 40 newtons as our net force. We have to use the x component of that 40 newtons. Okay? Because that is the component that matches the direction of the acceleration. And so instead of F net, I'm just actually looking for Fx, or Fa sub x, or whatever you want to say. It's the x component of my pulling force. That is going to equal mass times acceleration. So this is the same type of idea as whenever we've used F net equals ma. It's just that when I'm splitting F net into its parts, or when I'm expanding F net into the forces that are acting, I have to keep in mind what the acceleration is doing. Okay? Because if it's a horizontal acceleration, I need to use only x forces in my F net. If it's a vertical acceleration, I need to use only y components in my F net. Okay? And those are the two types that we're going to use. So, Fx, this component here, is going to be the cosine, right? Because this is the adjacent side, right over here. That's the adjacent side. This would be, I'm going to call this Fy. So here's Fx down here. Fx is doing the accelerating. Fy is not doing any accelerating. Okay, what Fy is doing, we're going to come up with later on. Okay, so Fx equals ma. That's the adjacent. I know the hypotenuse, and so then I'm going to use 40 newtons times the cosine of 30 degrees. And that equals my mass times acceleration. Okay, so I'm going to divide by mass to get the acceleration by itself, and it tells me the mass is 10 kilograms. So I'm doing 40 times the cosine of 30 divided by 10 kilograms. That will give me my acceleration. And when I put that together, I get 3.46 meters per second squared. If you're looking for significant figures, that should be correct, right? Because we've got 3 there, 3 there, 3 there. We've got 3 everywhere, so our final answer should have 3 significant figures as well. Now, I drew this box, and so the question doesn't give me any sort of direction reference, and so I'm just going to say that my direction here is forward. I'm assuming that I'm pulling it forward and not backwards. Now here's the second part. Calculate the normal force on the box. So usually on a level surface, the normal force is equal to the force of gravity, right? Because this box is not accelerating up or down. And since it is in equilibrium up and down, then the force of gravity pulling down must be equal to the normal force pushing up. Except in this case, there's another force pushing up, right? With my pulling force, I am pulling up with Fy as well. So in normal circumstances, where there's just a box sitting on the ground, you would say that F net equals ma, but vertically, a is 0 meters per second squared. And so then when we split F net into its pieces, we would have the force of gravity and the normal force. So because of that, we would know that the force of gravity and the normal force are equal to each other. But in this case, we also have Fy to take into account. So let's just say that up is positive. It doesn't really matter in this case. So we would have Fy plus Fn, the normal force, minus the force of gravity, so I'm inserting the direction of gravity already, equals 0 newtons. And so Fn, what I'm searching for, is equal to Fg minus Fy. Let me try this again. Fg minus Fy. There you go. Okay, so in normal circumstances, the normal force and gravity are equal to each other, but since I am pulling upward a little bit on this box, that means I am reducing the amount of support force that's required to counteract gravity. Does that make sense? So the force of gravity is pulling down, and normally it's balanced out by the normal force, but I, by pulling upward, am taking care of a little bit of that balancing out of gravity. So less is required of the normal force in order to counteract gravity. And so I get the normal force is equal to mg minus 40 times the sine of 30 degrees. Okay. So my normal force is equal to 10 kilograms times 9.8 meters per second squared, minus 40 times the sine of 30 degrees. This says 40. And when I finish that calculation out, I get 78 newtons. Upward. That's the normal force that's required to counteract gravity. So if we just do some quick mental math, 10 times 9.8, with the force of gravity, that's mass times 9.8, gives you 98 newtons. So gravity is pulling down with 98 newtons, and so 78 newtons of normal force makes sense when I am pulling upward a little bit. And that's the general idea of components of force.